Today we're taking a deep dive into the Radon transform, a type of Fourier transform that allows us to reconstruct the radiopharmaceutical of a patient given data from scanners. This transform allows for simple reconstructive techniques like back projection and filtered back projection. These are known as analytical reconstruction techniques. But the question is, can we do better than these? Well, it turns out we can, but we have to understand these basic techniques before we get into the more complicated ones.
All right, so we gave an initial lecture about tomographic image reconstruction. In the next two lectures, we're going to get more into the mathematical details and algorithmic details. And this first one is going to be about analytic reconstruction, whereas the next one will be about iterative reconstruction. So I want to especially acknowledge Dr. Anna Seller, who me and Carlos talked about at the beginning of this lecture extensively, and also Dr. Pedro Esquinas, who was co-teaching this lecture along with Anna. And we really appreciate the gracious sharing of the lecture notes. So today in this lecture, we're gonna focus on analytic reconstruction methods, and in the next lecture, we will focus on iterative reconstruction. So let's talk about imaging. In more conventional, planar imaging, you're basically taking an object and you're projecting it onto let's say a detector, a 2D detector. And so that's going to give you an image, but it's a 2D image, it's a 2D projection. So that's not giving you depth. However, in tomography, you do the projections at different angles, as for example, as you rotate a detector around the patient. So that gives you a series of projections at different angles, and then you reconstruct these into a volumetric 3D image as opposed to just a 2D image. So we've talked about some of these aspects before. So again, here's an example of a bone scan collected at different angles as the camera is rotating around the patient. And so the idea of image reconstruction is to take the projections and reconstruct them into a volumetric 3D image. For the purpose of this lecture, we're going to focus on a slice through the body. Of course, our body is 3D, but let's just focus on a 2D slice in our body, and can we reconstruct a 2D slice? So we're not going to focus on the axial dimension, though it can totally be extended. For example, if you are able to do this for one slice, then of course you could do it for the other slices. And even if you have oblique angles, etc., axially, as we have in 3D PET, then these formalisms can be extended. But let's just, to keep the discussion simple, let's focus on a 2D slice in the body. And think of a projection. Here's a line integral through the subject. And so this is a 1D projection at an angle theta of the object activity. So basically, you're taking a line integral through this 2D function. And then what you do is you can actually parameterize this line. So this line, and you can prove this easily, this line is given by this formula where S, which is the radial distance from this line passing through the center of the from the origin. So S is fixed and theta is fixed for this line. And having said that, then X and Y have a relationship. So then basically this ends up being a 2D integral where you're defining this delta function that says, I only want to integrate when I am along the, this line. So you basically transform this 1D integral into a 2D integral using this delta function. So then this actually is the Radon transform. So the Radon transform of a function, of a 2D function, is an integral through this function at an angle theta at a radial distance s from the system origin. So again, you're parameterizing this line, and essentially this line in 2Ds is defined by an angle theta and a radial distance s, and basically you write the Radon transform like this. So the question really is, and this is Radon, the person who he discovered this idea early on, and later, as we mentioned, it was independently also discovered by others. The question is, can you invert the Radon transform, because you're summing counts along each line, so it's not intuitive whether you can actually reconstruct each of these points in the inverse problem. So it might seem like a difficult problem, but it turns out you can actually do that if you're acquiring data along all angles. Now, there's this thing called a sinogram, and why do we call this sinogram? So we refer to data. If we plot data in the projection space as S versus theta, we refer to that as a sinogram. The reason is, if you just focus on a point source, let's say here or here or here or here, when you do this process, and you can sort of convince yourself by looking at this equation, if you have only a point source in the field of view with a fixed x and a fixed y, then you start to have an expression that has sines and cosines in it. And so you end up getting these projections. So the projections, as for example, you focus on this point source, as you rotate the camera around the subject at different angles, the S values passing through that point source end up giving you a sinusoidal curve. So that's why we call this kind of a way of recording data as sinogram, because you have these sinusoidal curves. And to convince yourself more, imagine you've got a point source here. You've got, for example, a SPECT camera here. So you do a measurement. But as you rotate it, the relative position that you measure this with respect to the center of the camera changes. So here, perhaps it was more closer to the center. Here, it's less close to the center, so it moves down. The center is here. And then as you do this, now it becomes more centered, et cetera, et cetera. So it moves around, and so you sort of get this sinusoidal curve. So forward projection of a point source, basically, where these are angles, and this is, let's say, the position, the S value, for example, would give you a sinusoidal curve. And so, of course, and now, since you're doing this for this particular slice, of course, now you can do it for the different slice. As you can think about these detectors going, actually along the body. So now in PET, it's a little bit different, because in PET, you're not rotating cameras around the patient. And also in some novel SPECT designs, as we've talked before, like pinhole designs, you're not rotating the camera around the patient. It might be stationary, or it might be, sampling the patients in a different way. But the point is, no matter how it is, you can always sort of generate sinograms. Because, for example, here, sure, you may have a detector that is receiving counts from many opposing detectors. But at the end of the day, you take this line, which is parallel here, and you also do these other lines for these other detectors. So all kinds of projections that are parallel to each other, you think of that as a projection, as though there was a detector here, like a flat, gamma camera that is rotating around the patient. But the beauty of PET is that this is all happening simultaneously. You don't need a physical collimator. Simultaneously, you're collecting data from, different angles within a single scan. This detector can be receiving counts from, different detectors, within a single scan, and there's no need for rotation. So you get different parallel lines that you imagine, and you connect the sort of dots between the different detector pairs. And so that defines your sinogram. So again, just thinking of, a number of detectors here, here's one angle, here's projection along another angle, projection at another angle. So you think of it that way. And also in PET, we have 3D PET when you, as we talked about before, when you remove the septa in PET imaging, you now can, this is an axial direction, the Z or the Z direction, going through the body like this, up and down the body. So now you've got these oblique angles. So again, we're moving beyond 2D. Now we're thinking of 3D. So again, for reconstruction purposes, right now we're thinking about this formalism where you're only looking at the 2D mode. And even if you have 3D mode, some people have in the past, come up with algorithms that transform a 3D data set into a 2D data set. They tend to be approximate methods or very difficult methods. But the point is, in reality, in PET, we're dealing with 3D mode. But again, for today's discussion, we're focusing on the 2D problem. But again, I want to emphasize this problem has been tackled in the 3D. And so, for example, we have 3D filter back projection algorithms, right? But for today's discussion, we focus on the 2D problem to keep it simple. So the core and the essence of image reconstruction, analytic image reconstruction, is the so-called projection slice theorem, also known as the central slice theorem or the Fourier slice theorem. And it's quite a surprising result, actually, and it's quite fascinating. And if you get this, you convince yourself that tomography works, that you can invert the radon transform. So think of an object here, and you're projecting it along a certain direction. Here, this is actually theta prime, because to be consistent with our previous slides, technically this would be theta. It is just consistency notation, but you could call this also theta. But to be consistent, let's call this theta prime, because this is really the angle would be theta, but that doesn't matter. You're projecting an object in a certain angle, whatever you want to call it. Okay, so you're projecting it this way, as I'm showing here. So the projection looks like this. This is a 1D projection, right? Imagine you've got a camera here, a gamma camera here. This is a projection you get. Well, what you do a 1D transform, 1D Fourier transform of this, you may get a signal like this. Now forget about everything I just said. Go back to this image. Now do 2D Fourier transform. Has nothing to do with projections. Just do a 2D Fourier transform. You may get an image like this. Now, if you draw a slice, and this is where the name projection slice comes to. If you draw a slice at the exact same angle that is shown here, through the 2D Fourier transform, you can prove that this slice's values is equal to this slice's values, which is the projection slice theorem. In other words, the 1D Fourier transform of a projection taken at a certain angle, theta or theta pi, whatever you want to call it, equals the central radial slice at the same angle of the 2D Fourier transform. Okay, so you have to keep thinking about this. This is actually quite a surprising result. And I'll show the proof in a second. But the point is, well, this means that if you now rotate your gamma camera, for example, around the subject, you're going to be slicing the Fourier domain at different angles. And so that way you can actually sample the entire Fourier domain by rotating your angle at different, by rotating your camera at different angles. Or effectively, this is what PET does too. You're collecting, within a single scan at different angles. So just to show you the same thing, you take the radon transform at a certain angle theta. You take the 1D Fourier transform of that, and you put all of these angles together at all these different angles. That actually gives you the 2D Fourier transform. So you do the inverse 2D Fourier transform. That actually gives you the image. So the projection slice theorem tells you that if you go through the steps, this gives you the reconstructed image. This slide I already showed you before. Just look at this formula here. This is just a formula for the radon transform. This is just a definition essentially of what a projection means. And then to just quickly show you the proof, and you can go through it carefully on your own, taking the 1D Fourier transform, making the substitution for the projection according to this formula, putting this in here, moving things around a little bit, and remembering the formulas for Fourier transform and the inverse Fourier transform. Sometimes people don't put the 4 pi r squared here. They put instead a 2 pi here and a 2 pi here. It's effectively the same. You go through the math. You can prove that you get this. In other words, when you go through this whole step, you can prove that by substituting the variables, you arrive at here. So you end up getting this formula, and f is just the inverse Fourier transform. Now this is in Cartesian coordinates, where u and v are the Fourier, equivalents of x and y axes. So go through the proof on your own and really convince yourself that this makes sense. And it's not a long proof, as you can see. Based on the projection slice theorem, we can actually come up with a number of reconstruction algorithms. So different ways to reconstruct the data. One is a Fourier reconstruction. One is filter back projection, which is the most popular. There's also convolution back projection. There's also a fourth one, which I'm not going to talk about, and that's back projection filtering, where you first project everything to the image domain and then you do the filtering, but I'm not going to talk about that. So I'm going to talk about these three algorithms and approaches to reconstruction. So let's talk about Fourier reconstruction. I think this one, by now, you've figured it out. We already said it in a sense. You obtain the projections from many different angles, and then you do the 1D Fourier transforms. That effectively means you're sampling your Fourier domain at these different slices. And then finally, you take this, because you've already sampled it, and you just interpolate between these. Because as you can see, as you get closer to the center of the Fourier domain, you approach the origin, you're sampling stuff more here, and you're sampling stuff less here. So you're going to have to do more more interpolation here than here. And then finally, when you do interpolation, that means you've sampled your Fourier domain. And so now you have a measurement of the 2D Fourier transform of your image. And so therefore, now you can take the inverse 2D Fourier transform, done, right? And notice, for those of you who are familiar with MRI, this is actually what we do in MRI exactly, right? So in MRI imaging, you're trying to sample the Fourier domain. There's different algorithms. You could do a spiral sampling and filling of the Fourier domain. Like you could start from here, and given your specific MRI sequence, you could do a spiral, or you could do different approaches. There is a way, even in MRI, to do this, to do radial sampling of the Fourier domain, which is equivalent to what tomography in a nuclear medicine sense, in a radon transform sense, is doing. So there's actually a way to do this. So there's a nice parallel there between MRI and this kind of a problem that we're tackling. Okay, so this is one way to do it. The problem is that you have to do the interpolation, because you got almost polar sampling, polar coordinates, but you got to do Cartesian grid interpolation. And then also the 2D inverse Fourier transform can be time consuming, relatively speaking. So the second method is filter back projection. For me to explain that, first I have to explain to you back projection. And we had a previous lecture when I talked to you about just the simplest method on earth of image reconstruction, or one of the simplest methods, just back projection. You don't do anything. You just back project all the counts, and you get blurry images. But mathematically, back projection is this function, where these are the projections at different angles. So this is a projection at an angle θ1 for different S values, for different radial positions. This is a projection at angle θ2 for different radial positions. And back projection means basically summing these integrals up. Or doing an integral over different angles. So for example, you pick a certain x and y value, let's say here, x and y, you fix x and y, you think about just x and y. Well, x and y for a given θ corresponds to a given s, so you look for those equivalent positions here, which might be this point, for a different angle, as you change theta, it might be this theta and S pair, and then you sum those up. So for the different theta and S pairs at different projections, you sum those up. So you're summing up this count and that count and the equivalent of it in these different angles. And so you sum all those up, that's back projection. And then you do that for this X and Y and this X and Y and this X and Y and this X and Y. So again, looking at this, by staring at this for a while, especially if you think of a fixed X and Y position, you know, any pixel within this image, and this summation, you start to convince yourself that this is a formula for back projection. Okay, so remember this formula that we were saying that method number one, we were doing Cartesian Fourier transform sampling and then doing the inverse Fourier transform. Well, let's go back to the polar coordinates. If you convert the coordinates from Cartesian to polar coordinates, you would remember that there is this theta is the angle and omega, sometimes also denoted as rho or as r, is a radial component in polar coordinates. Well, you would remember that this transformation from calculus into polar coordinates has this extra term, which is the Jacobian in the change of variables. And by the way, this is the ramp filter. So this Jacobian and this term that shows up here essentially okay, just hang in there, essentially becomes a ramp filter. So first of all, what does it even mean? The meaning is, because you're sampling things so much here and so little here, as you get farther away, as your omega value and your radial position away from the center increases, you have to do you have to increase the weight, because you're doing less and less sampling. So you're doing more and more sparse sampling at higher frequencies. So that weight that we have here essentially says, because because tomography is doing less sampling at higher frequencies, I have to fill that up. I have to help it out. It's not having enough sampling at higher frequencies. So I'm going to use that extra weight to fill that up. And that's the essence of the Jacobian actually is. So again, I'm just rewriting that formula that I showed you now with this extra term, this Jacobian term here. And you can now do this integration in two steps. First, you integrate along the radial component, the omega here. And then you do it along theta. Now, again, if you keep staring at this and sort of going through this and looking at it carefully, this second step is that thing I showed you, which is a back projection step, where you're summing over the angles. And this first one is actually a 1D, it's a 1D filtering step. So you're taking the projected and the Fourier transform. So you're taking the Fourier transformed 1D Fourier transform of the projection at a given angle, and now you're weighting it by the ramp filter and doing this operation. So this is a filtering step. This is you're filtering it using the ramp. And so if I can take you through the steps of the filter back projection, you first do 1D Fourier transform of a given projection profile to get this. Then you multiply this, because now you're in the Fourier domain, you multiply this by a ramp filter, which kind of looks like this. I'll tell you in a second why it's cut off here, because technically a ramp is supposed to, by strict definition, is supposed to go like this forever, but we cut it off here at the Nyquist frequency, which we'll talk about in a second. And then you do an inverse 1D Fourier transform, because you first weight it by this, and then you do the inverse Fourier transform. All right, and then once you're done, you do the back projection. So take a projection profile, 1D transform it, multiply it by the ramp to put more emphasis on the higher frequencies, because in tomographic acquisition, you're undersampling higher frequencies, so you have to help it out. So you weight it by this ramp filter, And then you do the inverse 1D Fourier transform. So now you've kind of helped it out, and now you can do the back projection. And so this is much better than just doing back projection. So pure back projection ignores all these 3 first steps and just does back projection. But here we said, no, we got to do this filtering first, then do the back projection. And then you do this for every angle, because we just did this for 1 angle. So here's an example of what might happen. This is with 2 angles only. When we've done filter back projection, 4 angles, 8 angles, 16 angles, 128 angles, and it starts to look really good. Whereas if you were not doing the filtering and you were just doing back projection, this is what you would get. So that filtered back projection definitely gives us better images and is mathematically very sound compared to back projection, which is not a very sound algorithm. Though it's kind of intuitive, but it's not an exact algorithm, and it definitely blurs the images, and we talked about this before. Now, in practice, okay, so this is a ramp filter, right? The problem with the ramp filter is that, one of the problems with the ramp filter is that at higher frequencies, it keeps amplifying signal more and more, which is correct. But if you have noise in your data, it also ends up, noise is higher frequency, so it ends up amplifying the noise. So in practice, as we talked about before, you may use different kind of filters to tackle the noise problem. And we had this slide in a prior talk, but basically the idea is that if you use an unmodified ramp filter, going like this, first you're amplifying the higher frequencies. And secondly, if the ramp filter allows frequencies above the maximum which are resolvable by the imaging system, this can introduce aliasing. So you can go back to the previous talks about aliasing, but essentially the units here are cycles per pixel. So the Nyquist frequency happens to be 0.5. So if you're actually, allowing frequencies beyond your detector's ability to sample your images, you're going to get aliasing artifacts. So that's why people cut off the ramp at 0.5. Okay, so people cut off the ramp at this is not the same unit, so just hang in there. You should always look at what the x-axis is. So if it's cycles per pixel, it should be cut off at 0.5. What I'm trying to show here is that different kinds of filters gives you different kinds of images, and it depends on the task. And as you use images that are having, that are damping the high frequency component of the ramp, you get smoother and smoother images, but you are losing resolution. So it's a trade-off, and we talked about this in the past. But going back to the aliasing problem, imagine these are your detectors, right? So these are the pixels in your detectors. 0.5 cycles per pixel says the maximum frequency I allow and I process is something like this, so that I can at least sample this twice, sample each cycle twice. So this is a Nyquist frequency. But if I'm allowing signals that are at higher frequencies, I don't have enough ability to sample this signal because my detectors are only like this, 1, 2, 3, 4, 5, 6, whereas this is moving really fast for me. So I'm not able to sample this twice per cycle, unlike this one. So I'm going to get aliasing artifacts. So here's an example of reconstructions where you are allowing those higher frequencies to come in, and you get this so-called, the Moore type defects, which is a form of aliasing. You see these kind of artifacts here, in the image, these kind of square-like artifacts. Okay, so this is when you allow those. So that's why we cut the ramp at 0.5. Okay. So this is what, again, so we cut the ramp at 0.5 cycles per pixel. But it turns out this ramp filter does have an equivalent in the spatial domain. So instead of taking things to the Fourier domain and multiplying by the ramp, technically you could do a convolution with this. So you take your 1D profile and you don't Fourier transform it, you just convolute it with this term. So there's an equivalent for that. And that brings us to the so-called convolution back projection algorithm. So instead of doing the 1D Fourier transform, multiply by the ramp, and then inverse 1D Fourier transform. We could just take the 1D Fourier with the 1D profile and just convolve that 1D projection by the spatial version of a ramp filter, or another filter you may want to use, and then you do back projection. Now, if you really want to look at the math of it, this is a ramp filter, and in the spatial domain, it looks like this. This first term is like the sinc function, but it's not just a sinc function, because sinc function is a Fourier equivalent of the step function, but this is not the step function. But it kind of feels like the sinc function, but it's not. Strictly speaking, it's not. But it kind of looks like it, but it's not. But it looks like this, right? So you take your 1D profiles and you convolute them with this term. That's your filter, and then you back project. Okay, so both of those are valid. In practice, people tend to do this approach. Okay, so you first take it to the 1D Fourier transform domain, and then you multiply it by the ramp, or a modified version of the ramp, where, for example, the higher frequencies have been further dampened, like we had here the Shep-Logan, the Han, different kinds of algorithms, or different kind of filters. Okay, so analytic reconstruction is amazing. The more you look at it, the more it inspires you and amazes you. But the question is, can we do even better than that? And the answer is a definite yes. And we're going to talk about iterative reconstruction methods next.